glad to introduce our next speaker, Ivan Fedorov. He is developer technology engineer at NVIDIA Russia, and he will tell us about advanced Vulkan. Good luck.
I'll begin with a question, why Vulkan? Our next subject will be multi-threading and common buffer recording. Then we will talk about resource state tracking and how you can efficiently do that. After that, we will talk about work submission, and the last subject is memory management. And after that, there will be a few words in conclusion. If you have any questions, please do not hesitate to ask them after the presentation. The first subject is why Vulkan. It's a modern multi-platform low-level graphics API. It supports extensions and layers, where extensions are cool because you can quickly get access to new hardware features, and layers are cool because you can extend existing API with additional validation or features. It's important to mention that Vulkan is designed for high-performance applications. Vulkan has low CPU overhead compared to traditional graphics APIs. Many things are done on application side instead of driver side. Vulkan is designed for multi-threading. There is no thread-bound functions as in DXGI. All functions can be called from any thread. The specification explicitly indicates which and how functions must be synchronized. Vulkan is more explicit compared to DX11 or GL. Many things that were hidden now are explicitly controlled on application side. And the last major reason to use Vulkan is cutting-edge hardware features. Now we're going to talk about common buffer recording. When an application records a command buffer, the driver translates the comments and writes a native GPU command buffer. We call it push buffer. This allows the driver to avoid any command post-processing at work submission time. Now let's define the problem. From driver perspective, most of the rendering time on CPU is taken by command buffer recording. There are two options that can be used to solve the problem. The first one is command buffer reuse. Surprisingly, no one uses that. And the second option is multi-threaded recording, about which we're going to talk a bit later. Here are a couple of good examples for command buffer use. Post-processing can be completely pre-recorded if it doesn't change frequently. Usually it doesn't take much time on CPU, but it depends on the complexity. Also, you can reuse command buffers in shadow map rendering. In the case of localized source, it's trivial. You can just check that the list of dynamic objects is the same as on the previous frame. Secondary command buffers are also translated into push buffers during recording. And this allows you to record a group of commands once and use it multiple times. For example, if you have a scene object which consists of dozens of draw calls, and you know that it will be visible for more than one frame, in this case, it makes sense to record a secondary command buffer. Moving to optimization of command buffer recording. This image shows an example of how commands are processed in DX11 and OpenGL. The application thread sends the commands to the driver thread, where they are processed asynchronously. In the case of Vulkan, all commands are processed in the calling thread. The issue with parallelizing the processing of rendering commands should be solved on the application side. The design of Vulkan allows it to be more efficient on the CPU side compared to traditional graphics APIs. Here's an image which shows the worst case. We see this from time to time in games. The rendering is single-threaded, and the performance is render-thread limited. It's better to avoid using the concept of main render thread. It causes underutilization of CPU. Worker threads are waiting or idling while the main render thread is doing serial work. Here's an example of what it looks like in most cases. It's clearly visible in the profiler when an application uses main render thread concept. You can see gaps in the execution of worker threads, which are caused by serial work in the main render thread. The pipeline for common buffer recording goes as follows. First of all, allocate a common buffer, then begin it, then record comments, and then close it. Avoid doing any of this outside of the recording thread. We have seen the X12 game where the main render thread was calling begin and end in the main render thread, while command recording was parallelized. This caused plus 1.1 milliseconds per frame added specifically to the main render thread. Next will be an example of multi-threading typical rendering pipeline. Here's an example of rendering pipeline. You can see here different render stages, shadow map rendering, gbuffer fill, and others. Let's define the render stage as some amount of render work, data preparation, and common buffer recording. Here's how rendering is typically parallelized. Render work of each render stage is split into a number of parts, and these parts are processed concurrently in multiple threads. The part which finishes executing the last one runs in the next render stage. Here you can see two separate render stages. Each stage renders a number of objects, and there are only two CPU cores to keep it simple. Using the number of objects, the render stages can be divided into parts and processed in parallel. Here's how it looks. Now there are two parts of each render stage, and these parts are processed in parallel. Moving to resource state transitions. First of all, let's define the issue. Batching of pipeline bearers affects GPU performance. Each individual pipeline bearer may cause GPU pipeline flush. That means that the commands after the bearer cannot be processed until the previous commands finished execution. To minimize the number of potential flushes, the pipeline bearers can be batched together. Resource state tracking is a non-trivial issue in multi-threaded render. There are three common ways: default state, at the last moment, and render stage dependency tracking, which is usually associated with render graph. Let's start with default state approach. Basically, you just choose the default state for a resource, and after any change, you make a transition back to the default state. Here you can see two shadow map render stages, which we spoke about earlier. Let's count that default state for shadow map is read-only access from shaders. At the beginning of the first part, there is a transition from the default state to the required one, which in this case is depth right optimal state. Then at the end of the second part of the render stage, there is a transition back from right optimal to the default state. And you can see here 4 individual pipeline bearers. Pros and cons for this approach. The bearer batching is pretty bad. This approach may also cause redundant transitions, but there's one good feature. It allows to process render stages on CPU in order different from order of execution on GPU, due to the fact that you know the resource states. It's pretty good because you can divide render stages into parts and launch them for processing old ones. Now let's talk about at the last moment approach. The idea here is to track resource states as part of the resources and to make resource transitions right before its usage. Here you can see that there is a new render stage for pass. It's required to show where happens the transition from right optimal to read-only state. You can see transitions from read-only to right optimal at the beginning of each shadow map render stage, but the transition from right optimal to read-only are batched together and occur at the beginning of the forward pass. You also can see that there are gaps in execution of threads between render stages, and that's the limitation of this approach. Pros and cons. The bearer batching is better in this approach, and it doesn't cause redundant transitions, but it doesn't allow to process different render stages in parallel or out of order, just because you need to change states in the order of execution on GPU. Now let's take a look at how bearers look with the third approach. You can see that there are only 2 pipeline bearers, all transitions are batched, and there are no gaps in execution of threads. What's render graph? In render graph, each node is a render stage, and each node has dependencies, inputs and outputs, where each dependency is marked with access type, read, write, or both. The forward pass in this example requires scene depth, shadow map, ambient occlusion map, and it produces a color map. Here's what it looks like when other nodes which produce the required inputs for the forward pass are present. You can see two nodes, depth prepass and shadows, which have no input dependencies, and therefore they can be executed in any order. But the order of other two nodes is explicitly defined by their input dependencies. Here the nodes are ordered for serial execution with regard to their dependencies. Now let's take a look at the barriers. Each node has its own list of required transitions. Just for simplification, there is no such list for forward pass. Now, what if we move transitions to the left side as much as possible? You can see that there is nothing that prevents moving the transitions from the list of shadow rendering node to the list of depth prepass node. The same is true for ambient occlusion map transition. Now, there are only two pipeline barriers, no redundant transitions, and it's known where and what transitions must be performed. Pros and cons for render graph. The barrier batching is perfect. The approach doesn't cause redundant transitions, and it allows to process render stages in any order and concurrently. There are also additional advantages. Render graph solves an issue with resource reuse because you can determine at what point which resources are utilized. It simplifies multi-queue scheduling. You can just assign a node to a different queue and use dependencies for synchronization. And with render graph, you don't need to keep in mind all places where resources are accessed and how they're accessed. That's especially difficult when there are two render pipelines, one with a synchronous compute and the other without, or when some render stages can be toggled on and off in runtime. You can read more about render graph in Yuri O'Donnell's GDC 2017 presentation, Frame Graph Extensible Rendering Architecture in Frostbite. Now we're going to talk about work submission CPU overhead. VKQ submit is a price operation on CPU. It takes about 21 microseconds on a high-end CPU, and the number of command buffers doesn't affect the time. But 50 calls per frame take about 1 millisecond, which is 6% of the frame for 60 FPS target. Here's what it looks like in DX12 and Vulkan. In DX12, there is no way to batch work submission together if there is a synchronization between submissions. We've seen a DX12 game which was CPU limited because of too fine-grained work submission. There was about 65 queue submissions per frame, which takes 1.8 milliseconds per frame in DX12, and that's about 11% of the frame for 60 FPS target. This number of submissions is affected by the number of used queues and the amount of synchronization between queues. In Vulkan, work submission can be batched together, even if there is synchronization between submissions. VKQ submit takes a list of VK submit info structs, where each struct has lists of common buffers, wait semaphores, and signal semaphores. 20 submissions batched together take about 183 microseconds, and it means that one submission takes about 9 microseconds, which is 2 times faster than individual submissions. You need to keep in mind that the more queues are used, the more submissions are required. As I mentioned before, the functions in Vulkan aren't thread-bound. Therefore, work can be sent from any thread, but there must be synchronization to avoid concurrent submission from multiple threads to the same queue. It's important to mention that work must be submitted in the correct order. If there is a submission which has a wait semaphore, there must be a submission previous that which signals the semaphore. Input to screen latency can be decreased in CPU-bound case with intermediate submissions. It's important to remember that too many submissions is bad due to overhead on CPU, so it's better to keep the number about 5 to 10 submissions per queue per frame. Here's an example of the latency in the CPU-bound case. Let's assume that the input is processed at the beginning of the frame. In this case, the latency is sum of CPU frame and GPU frame. If the work submission is divided into 5 intermediate submissions, where each submission occurs as early as possible, the latency can be significantly lower compared to the case where work is submitted once at the end of the frame. The next subject is synchronization primitives. There are 3 synchronization primitives in Vulkan: semaphores for queue-to-queue synchronization, fences for queue-to-host synchronization, and events for host-to-queue and queue-to-host synchronization. Semaphores can be used to synchronize execution of work submissions in multiple queues from the same or different families. The signal operation sets a semaphore into a signaled state. The wait operation sets it back to unsignaled state. There is no direct control in the state of semaphore. Fences can be used to track on host the execution of whole batch of submissions submitted with VKQ submit on GPU. Typical use case, specify one at the last VKQ submit in the frame and use it for common buffer resetting, read-back buffer readiness, and resource release. Fence must be manually reset on host to set it to unsignaled state. Event can be signaled or wait on GPU in a common buffer and can be signaled or checked for the state on host. Events can be used for fine-grained synchronization with host. For example, you can use it to check the processing of some resource has finished on GPU, and you can do something with it on host asynchronously to rendering. Moving to walkthrough of memory allocation. In Vulkan, an application has an explicit control on memory management of images and buffers. And that means that an application must take responsibility for efficient memory management. Vulkan exposes a number of memory types and memory heaps, where each memory type has memory properties and memory heap index. The configuration of heaps and types isn't fixed, and an application cannot rely on some specific configuration. Memory requirements must be requested for all buffers and images, and memory must be allocated using the requirements. For example, depth stencil attachments may have different requirements compared to regular read-only textures. Vulkan supports resource aliasing, which means that different resources can be bound to the same range of memory, but it's important to keep in mind that it may prevent color and depth stencil attachment compression and efficient page table usage. There is an extension which solves this issue. It's called dedicated allocation. It can be used to explicitly define that there will not be any aliasing for the allocated memory. And in bandwidth-limited applications, we observed about 15% improvement. How to use it? Color and depth stencil attachments are good candidates for dedicated allocation. Also, it can be useful in the case of very large buffers or images with the size of dozens megabytes. In other cases, it's better to use regular allocations. Now let's take a look at the memory allocation concept. First of all, check whether the dedicated allocation is required for the resource. There's an extension which can be used for that. Then you find proper memory type using the memory requirements of the resource. Then using the heap index from memory type, you may want to check whether there's enough memory for the allocation. The next step is memory allocation. But keep in mind that VK allocate memory can return out of memory due to fragmentation, for instance. And the last step is memory binding. The last subject is an efficient memory allocation. Memory allocation and binding are expensive operations. It's better to avoid doing allocations for an individual resource without a serious reason for that. Also, avoid creating multiple resources when it's possible to suballocate a single resource, because resource suballocation doesn't require memory allocation and binding. Each of these two functions may take from 10 microseconds up to 300 microseconds on CPU. Therefore, it's important to create resources asynchronously to rendering. Memory is allocated in pages. Therefore, when the memory is allocated for a small individual resource, it's a waste of memory. Here's an image which shows typical issues. In the topmost case, there are 3 separate allocations for 3 separate resources. It's pretty bad due to cost on CPU and possible waste of memory due to fragmentation that I mentioned on the previous slide. And the next case is better, but there are still 3 separate resources. And the last case is perfect due to resource suballocation. To recycle the allocated memory, you can destroy a resource and bind another one to its memory range. And allocation reuse is faster than reallocation. Resource memory alignment must be taken into account when application binds a resource to the memory. Resources placed in a continuous chunk of memory can enjoy better cache utilization. It's better to keep the number of memory allocations as small as possible. Ideally, stay below 1024 allocations to reduce overhead on Windows 7. There's also the maximum number of memory allocations in device limits. And now moving to a few words in conclusion. Vulkan exposes nice features which can be used to make rendering more efficient compared to other graphics APIs, but it requires a lot of low-level management on application side. If you have any questions regarding the topics elaborated in the presentation, feel free to ask me.
Thank you, Ivan. Now it's time for questions.
Hello, thanks very much for the talk. It was pretty insightful. But one thing that you didn't seem to touch on much when talking about the resource transitions, like versus DX12, Vulkan gives you source and destination flags for being able to say which part of the pipeline that you wish to flush to and from. Does being more specific with that rather than just be flush the whole thing, does it actually give any practical performance improvements, or is it more of a it might in future kind of thing?
Well, right now, well, unfortunately, I don't have exact information about that. I just haven't checked that yet. But it seems, I think most likely it doesn't matter actually, at least right now. But I'll keep in mind your question, and maybe we'll write something about that in do's and don'ts for Vulkan or article. Yeah, interesting question. Thank you.
Thanks very much.
I'm not very familiar with Vulkan, but you talked about memory requirements. Do we have to care about tiling when we allocate for textures, or is it done by the driver? I mean,
yes. Well, actually, there may be different requirements for resources which require tiling and linear and non-linear resources. But it's also possible that they can be in the same heap. But there is image buffer granularity, which defines the granularity at which linear and non-linear resources can be bound. Yeah, that's it.
Any more questions?
Hello. Almost everything that you said is as much applicable to Direct3D 12 as to Vulkan. And why have you named your presentation Vulkan and not next generation APIs?
Well, actually, there are a lot of Vulkan-specific things. For example, secondary command buffers in Vulkan are actually translated into push buffers, and in DX12 they're not translated. There's an emulation. Also, memory management is very different compared to DX12, just because of all these, heap memory type configurations. Well, yeah, also work submission batching and overhead, all this is very specific to Vulkan, so I don't know. In my opinion, it's more about Vulkan rather than about all low-level graphics APIs. But yes, for example, resource state tracking is also the same for DX12.
Thank you.
Thank you.
Any more questions?
Можно по-русски спрашивать?
Could you please ask my question in Russian? Thank you. I've seen the figures concerning one game, another game. Could you please describe the whole picture? How much more effective is Vulkan compared to DX12 for heavy games, for heavy-duty games?
Many games that use Vulkan right now, so there is like a lot more information about DX12 rather than about Vulkan. Well, yeah, only like Wolfenstein and yeah, Doom. Well, they don't have DX12, so it's hard to compare. Just Vulkan has some like improvements compared to DX12, and yeah, it looks like it can be better in terms of performance. Oh, sorry. Well, it's again hard to compare. Well, in general, just low-level graphics APIs require a lot of, efforts to make it efficient, and in most cases, like DX11 is a nice graphics API because it's easy to use and it's like fail-proof in most cases. And Vulkan requires a lot of tweaking and like vendor-specific code passes. So I just think that there's a lot more can be achieved with Vulkan, but no projects that I can like provide as an example.
Я тоже по-русски спрошу, с вашего позволения.
I would like to ask a question in Russian as well. Thank you. As far as I know, Windows 7 has a behavior. If the GPU lacks the memory, then Windows starts silently copying data from the GPU memory to dedicated memory. Is there any solution for this in Vulkan to work around this Windows behavior?
Like driver does nothing for you in this case. You just get out of memory when you allocate memory. But like in general, all memory management goes through operating system. So Windows manages actually memory, and it can transfer your resources, your data, your buffers from GPU memory to CPU memory, just to give resources to another process. And there is no way to avoid that.
И второй вопрос, если вы не возражаете.
Second question as well, if you don't mind, if I understand it correct, when creating such an object like pipeline state object or something analog in Vulkan, we transfer the shader object as a binary format, and when we validate it, it is exported to vice code of the machine we're working with. So the assembler, who is typical for this video card,
And state object is created, the shader is translated to some language. Yeah.
И вот вопрос, собственно говоря,
and the question is actually, are the shader duplicated if they are the same? Like we create different two pipeline state objects and we transmit this same shaders in a way.
When you create a pipeline state object in Vulkan, you pass like already compiled shader model. So you just created separately shader models, and you pass it to pipeline creation. So it's all, again, on application side. You can create one model and create 100 pipeline state objects using this model.
Привет, я тоже по-русски.
Well, I would like to ask a question in Russian as well. I have a lot of questions actually, but I would like to ask a few. First, we know specific peculiarities of NVIDIA. Graphics pipeline layout has a cache. It is there in the Vulkan IP, but with AMD, the guys say that you better not use it because it actually does not give any benefits. It doesn't bring you anything. With NVIDIA, does it make sense using this cache, saving it to the disk after creating all the pipeline state objects, and then load it in case?
Exact information about this. Again, I'll ask guys around.
Тогда другой вопрос.
Another question then. You have a memory visible in the CPU, GPU. 256 megabyte is the limit there, and if we pass to this something over 256 mega, we have to submit it to the queue, wait for the result, wait for it to be cleared, clear resources, and fill it again. With NVIDIA, how is the memory working? How is the memory functioning? Or there's also a limit of 256 and...
Actually, you can request the information about heap size, host local memory, cached or coherent, requested through a graphics API, through the interface, and get the value.
Окей. То есть это...
That means that the data shown there is valid and you can use it.
You can even create resources and host memory. I don't know, like there are many ways to interact. So yeah, actually there are separate, our driver actually exposes special memory types for images and buffers, I believe, which allow creation in host local memory with like access. GPU can access this memory, but it's more like for memory over commitment management. But maybe you can use it in any way. I don't know. Not sure.
Еще такой вопрос.
Another question then. The bundling of resources. Like we have the different descriptor sets. So with AMD, we have a strict recommendation not over a maximum of 4 descriptor sets per shader. Other recommendations from NVIDIA?
I know 4 or 5, something like that. It's better to keep the number of descriptor sets as low as possible, as little.
Okay.
And the last one, maybe. I have a lot of them, actually, but the last for now. There is a thing like push constants. How fast are they in NVIDIA compared to dynamic buffers over offsets? And another question then about the buffers. Are those offsets limited by 64K of data?
They're
Ладно,
not
тогда
limited.
про push constant.
All right, push constants. Any information? How fast are them, or you better not use them? Because they are included in the pipeline state object, and this has to be.
For per draw call data changes, you can use them. Yeah, they're cool.
То есть они быстрые.
That means they're fast. You haven't used it.
Actually, like in any case, it's better to to measure the difference to performance because from driver to driver, this may change. From architecture to architecture, this may change. So, like in any case, it's better to check.
А у NVIDIA много.
Are there any different architectures of NVIDIA drivers?
Kepler, Pascal,
И на все.
And every architecture behaves differently.
it should be pretty identical. I'm just like thinking that there can be different behavior, like with memory types, memory heaps on different architectures. There's different configuration. So it's better just not to rely on some fact that this is just a great way to do some things. This may change.
Ага, спасибо.
Thank you.
While I am bringing the microphone to another questioner, I have an announcement. Please give in your portable translators after the party. По-русски сдайте, пожалуйста, переводчик.
So don't forget to hand in the handsets after we are through with the session.
В данный момент
Right now, the driver NVIDIA for Fermi architecture supports 12X. It happened on the 3rd of July. And will there be the support of Vulkan for the old architecture?
Thank you.
Okay, anyone else?
Just on the off chance, on DX12 there's execute indirect, and with Vulkan, with the NVIDIA extension, you can do device-generated commands. But do you know if on the horizon there's any chance that there'll be a cross-vendor KHR extension for it, or if I just shouldn't hold my breath on that one?
Yes, we hope that device-generated commands will become like shared across all vendors. I know, like KHR extension.
We have still plenty of time, so you're free to ask. Okay, anyway, you can always ask in private. So thank you, Ivan.
Thanks for your attention.
And this was the last presentation of our forum. So we were glad to see you here. And until next time, thank you very much.
here with another one of the participants on 4C. Hi, please introduce yourself.
Hi, I'm Jean-Philippe Morel from Ubisoft Montreal. I'm working on Rainbow Six Siege.
Very nice. What was your first video game ever? Do you remember it?
Oh my God. I did a port of a very, oh no, I don't want to talk about it. It was called War Chess. I don't know if anyone knows about it, but it's just a port of a PC game to console game on PS2 like 15 years ago. But my first real game, I would say, was I worked on Prince of Persia, several Prince of Persia at Ubisoft.
That's very nice. What was your first video game that you've played?
Oh, the first that I've played? Oh. On the Atari 200. I don't know if I say it correctly in English. It was called Smurf.
That's an old one.
Yeah, it's a real old one. Yeah, it's an old one.
And well, now that the time has passed, what's your favorite video game of all time? Do you have one?
Of all time? Oh my God, that's a good question. I would say I spent a lot of time playing Unreal Tournament a while ago, but yeah, Unreal.
The very first one?
Yeah, the very first one. Yeah.
Absolutely. What led you to the video game industry? How did you come here?
Oh, it's a technical challenge. The technical challenge is I first wanted to make graphics, but I realized that was not really my thing. I like to build machines, like machines that can scale, that can live for a long time. The technical challenges in video game industry is.
Now that you're in it, what's your favorite thing about the industry? What do you like most about it?
It's the same thing, exactly what I said. It's building machines, building bigger machines, machines that scales. I'm not even that interested in the nature of the game. That may disappoint you, but it's more the machine that I'm building that interests me. And I have a lot of creative people around me to make some good games.
So it's the technical side of things that you're into?
Exactly.
All right. So anything you particularly don't like about the modern state of the industry, maybe?
I worked with really big teams. It's not really that I don't like them, but I prefer some smaller scale team, probably. But that's the first thing that comes to my mind. What else? Oh, that's pretty much what I'm thinking about now.
Fair enough. Let's make some predictions. What do you think will be the new thing, the new big thing, the new trend in the gaming industry in like 10 years' time?
Oh, in 10 years' time? Well, I won't say it's new, but I think there will be more and more games that lives for a very long time, that evolves that over time, and I think that's a trend that will continue over the next years.
Do you think it will be like a breakthrough point through some game, or it's just going to be like a slow progressional evolution into this state?
I think it's going to be a slow evolution, and I think it's going to be a slow evolution mostly because we need to adapt to that kind of mentality in the game industry, and
fair enough. If you had absolute creative freedom, which I don't know, maybe you have, but still, like absolute creative, financial, professional freedom, what game would you like to have made?
I will keep that secret if you don't mind.
We almost had an announcement here.
I have good ideas, but I will keep that for myself.
Okay, but that's a secret then. Is it a secret on what do you think is more important in games, like graphics or gameplay, or maybe the storytelling?
No, I think it's everything is building a community and make it that community grows and grows and grows, and make that community grows over time, and so we can build on that for many years on the same kind of titles.
Okay, great. Let's return to the real world for a second from video games. We're in St. Petersburg. What do you think about the city?
Oh, we had a good time yesterday. I was just trying to find good place to go, and it's awesome. We had a tour of the whole city. We had a boat trip. It was awesome. It was awesome, really.
Right. What about the event itself for C? I know it just started, but still, any impressions?
Oh, I can't wait to see. I can't wait to see the talk Friday and Saturday. I want to know more about what people think about the future of gaming industry.
Maybe something specific you're looking forward to, some specific speech or lecture?
Yeah, I'm very interested about monetization. How monetization, I told you I like big machines, build big machines, and monetization is something that we need to learn a lot. How it works, how we integrate that to game, and I'd like to see how other developers are doing that. Some massive online infrastructure. Also, I want to see. I want to hear more about that. How people doing that.
If you were interviewing yourself right now instead of me, what would you ask yourself?
At what time is the party? Saturday?
Well, I guess you'll have to answer this question yourself. Either way, I have you have a great time at the party, and you have a great time at the event itself. Thank you very much for sharing.
Thank you very much.
So we keep catching our speakers in the hallway and putting cameras in front of them. Hi, please introduce yourself.
My name is Samuel Ranteskla. I work for Microsoft as a principal program manager out of Sweden.
Okay, Samuel, so let's talk about games. What's your favorite game?
Well, I wish I played a lot more games than I actually do. So I have to go back into the past. Like one of my really favorite games is Jag the Lions 2 from like 92, 93. I think it was made here in Russia, if I'm not mistaken. Civilization, always been a big fan of that. And then the Enemy Unknown UFO trilogy from the 90s. There's so many games, I mean, it's like impossible to select one. But they're all strategic games, the ones that are my favorite.
Yeah, you're obviously a tactician. That's commendable. But do you remember the very first game you've ever played?
Decathlon, probably on the X86, somewhere around 84.
Wow, that's... I don't even remember that one.
It's like you basically play Decathlon and you just hammer at the keyboard to go faster, like 10 different sports events. Played it like crazy. I was 8 years old then.
Wow. How did you get into the gaming industry?
It was by chance, actually. So I was studying at Uppsala University, doing computer science, and they had this fair where companies were meeting the students. And there was these two guys that they've started a game company in the basement, and they wanted somebody to write a BSP tree, binary space partitioning tree. And I was looking for my thesis, so I figured let's combine those. So I joined them, I wrote my thesis in the games industry, and then from there on kind of like just went on. So this was 2000.
But now in 2017, what's your favorite and least favorite thing about game dev?
I mean, I think the games industry is awesome. Great place to work. There's so much passion. There's skilled, very intelligent people. I think that's my favorite thing. The least favorite thing is that, which I covered in my speech a little bit, I think that we're looking a little bit too much at how do we turn time into money, rather than seeing like how do we educate our kids. I really want to, that's my passion myself, is like take this experience, make our kids better tomorrow than they are today. I'm a parent as well, so that's coming from that.
Well, that's a very noble thing to do.
I don't know if noble, just I think it would be a good thing for us.
Definitely is. About your speech, did you have any interesting questions that maybe stood out?
Yeah, there was some interesting questions, like if we look at mixed reality, what's going to happen with that? What's the dangers with that? I couldn't really answer them because let's see what happens.
But if you were a part of your own audience, what question would you like to ask yourself?
That was a tricky one. Are you sure that you're right?
Are you?
No.
Well, we can be sure 100%, but still, we're trying to foresee the future here. How do you like the conference?
Love it. St. Petersburg, great place. Wargaming, excellent hosts. It's a great place to be. You should come to the next one.
Definitely do. Say, if you had the chance to go back in time to when you just started working in the industry and give yourself one advice, what would it be?
Try one of your ideas out.
That's very good. Thank you very much, Samuel. I hope you like the conference. Thank you.
Thank you.